Hi guys, welcome back to the Astro Imaging channel. Today's session is on optical theory by John Hayes, and John's in the room. I'm sure he's got a great presentation, but of course, as always, before we jump into that, we have our image of the week. And this week's image of the week is by Richard Flynn, one of the mods in the Cloudy Nights forum. And it's a beautiful image, and I'm going to pull it up right now. First, I have to do that. And Richard was not able to be in the room tonight, so Josh is going to read his blurb. And I hope you can see it there. Looks like you can, yes. Beautiful Coma galaxy cluster. Go ahead, Josh, if you wouldn't mind.
Yep. Okay, so Richard sent a note over, and this is what he said about his image. He says, I've always loved these galaxy clusters, and the Coma cluster, or Able 1656, is definitely my favorite. It contains over 1,000 identified galaxies, with about 800 of them within a 100 by 100 arc-minute area of the celestial sphere. The cluster of galaxies has a mean distance of 321 million light-years from Earth. I shot this cluster using my 8-inch RC in the AP-CCD-T67 telecompressor. Most of the galaxies are older ellipticals within the cluster's core, with some spirals on the outer areas. I chose the telecompressor so I could get in NGC 4921, the barred spiral in the lower left of the frame. The total integration time was about 11.25 hours, with 33 luminance subs of 900 seconds and 12 times 300 seconds of RGB. I used the Astrodon Gen 2 E-Series filters and shot everything unbinned at 1 by 1 with the SBIG STF 8300M set to -20C. And that is it. So congratulations, Richard. Awesome picture.
Yeah, that's a great picture. Lots of galaxies there. I love those pictures. That's one that I want to solve in PixInsight and just see all the circles pop up.
Just to follow up on that, Adam, so we had a question tonight about how to submit to the Image of the Week contest, and just to let everyone know, for now, the way we're running with this is that we have a Image of the Week submissions post on Google+, and we are keeping it as sort of a rolling submission, so if you can submit at any time, and we'll send a new post out every once in a while, but we go over all the pictures from the last few weeks at least and select from there. So you can submit there anytime, and we will see it, and it'll definitely be up for consideration.
Yep, and I'm actually wondering if we can reshare that. Maybe we might be able to reshare that so it pops up on top of everyone's screen.
Yep.
If so, I'm going to do that right now. But without any further ado, we have John in the room, and John, are you there?
I am here. Can you hear me?
We can hear you. You're welcome to take it away.
Good, good. Well, my name's John Hayes, and you know, I want to thank Adam for inviting me to come speak to you guys. I'm delighted that you're interested in optics, and you want to learn something a little bit about some basic optics, which we'll go over tonight. And I'm gonna try and share my screen here, and let me see if we can do this easily here. So bear with me here while I pull this up, and let's see if that works. You should be able to see that. Can you guys see that okay?
Right now I'm just seeing your avatar, but give it a second. Sometimes it pops up. Are you guys seeing his screen? Or?
Yep, I can see it. First order optics, PowerPoint.
Great, great. Okay. All right, well, before we dive into this, we're going to talk a little bit about first order optics tonight. And you know, when I'm on Cloudy Nights, I see lots of discussions about optics, and I know there are a lot of folks on Cloudy Nights who know a lot about optics, and there's pretty much a wide range of knowledge. I mean, some folks know a lot, some folks don't know very much, and I see a lot of confusion, so I'm delighted to get to talk a little bit about this. But before I do that, before we dive into this, I thought I'd just tell you where I came from. I started building telescopes back in, oh gosh, 8th grade or so. I built an 8-inch Newtonian back then, back in the 60s. And then in high school, I built a 12.5-inch Newtonian Cassegrain. And in graduate school, we had a fun class. Believe it or not, it was actually for credit. I thought it was so much fun. I could go in and use all the machines in the optics shop and build whatever I wanted to. So I built an 8-inch Newtonian Cassegrain there and had a lot of fun doing that. My undergraduate degree is from the University of Arizona in astronomy and physics, although I have to admit to you guys, I probably don't remember anything from astronomy. You guys can probably teach me a lot in astronomy, even though I have a degree in it. But my real degree is my graduate degrees are in optics from the Optical Sciences College at U of A. And I spent about I spent about 25 years as a full-time optical engineer, working at Wyco. I was an owner and director with Jim Wyant and some other folks. And my real job while I was there was to engineer new products, and built lots of interferometers, and got to have a lot of fun building an AFM, atomic force microscope, factory test equipment, wrote lots of software, and then went on to become a research professor at the University of Arizona, and only lasted a little while because I like starting companies, and I started another company called 4D Technology, which makes very high-speed interferometers, and I ran that for about 5 years and got tired finally, and retired, and I'm still on the board there. And I say I'm sort of retired because I still do consulting in optical engineering and product development, and I write for Plane and Pilot magazine. I'm a technical rock climber. I do astrophotography. You've seen me on cloudy nights with my C14. I'm a flight instructor, so I'm always pretty busy. But let's go ahead with that. Let's talk a little bit about optical theories, and I'm going to try to make this interesting for you guys. I don't want to scare you off with these complicated-looking slides, but we're going to talk a little bit about this, and I'm going to work to try and make this very, very simple in the end. But when we talk about optical theories and we talk about how do we understand how light goes through an optical system, there are different theories, and we start with geometrical optics. We then move to scalar wave theory, which is physical optics, which includes diffraction theory, and you guys have seen a lot of that stuff. Electromagnetic theory, which is the vector wave theory of light, E&M, and then we get into quantum theory of optics, wave particle theory of optics. It can get very complicated. But in terms of optical design and engineering, this list is in order of decreasing usefulness. It's the one at the very top. Geometrical optics is really the important thing, and it's a huge subject. We're only going to talk tonight for maybe an hour, but it's really the only means by which the basic properties of an optical system can be designed and described. And as we'll see, first-order optics, which is kind of the title of this talk, is really equal to Gaussian optics, which is the same as paraxial optics. And I'll tell you what the differences are.
John, can I interrupt you for 1 second?
Yeah.
We are seeing your PowerPoint screen, but not your shared presentation. And I think you're intending to share your presentation. Is that the case?
When you say the shared presentation, I'm trying to show you the PowerPoint screen, which is full screen on my. And now you're seeing my entire screen there, I hope.
No, we're not seeing full screen. We're still seeing. I see optical theories right now, but.
Yeah. Uh-huh. And what do you see? I'm sorry.
I'm sorry. I see your PowerPoint, your full PowerPoint screen, like home themes, tables. So I don't see this full screen. It's fine if that's the way you're intending, though.
Yeah, I was trying to just go full screen there, just to make it big enough to see, because we're going to look at some diagrams and that sort of thing. So it's going to be hard if I shrink this down, but I do want to make sure you can see it okay.
John, are you just sharing the individual application itself, or are you sharing your entire desktop?
I was sharing the entire desktop, so maybe that's the problem. Right now,
try pressing. What's full screen? F5 or what's full screen share in PowerPoint? Oh, he's got a Mac. I don't know.
Yeah, I've got a Mac. I just do that, and that's the entire screen. Can you see that entire slide?
We see the whole slide. We don't see it in like presentation form, but I can see the whole slide, so that's fine.
Oh, that's interesting. Yeah. Well, I apologize. What I'm seeing looks correct, so I don't know how to correct it for what you guys are seeing. I'll tell you what. Let's try this. And can you see the whole slide there from PowerPoint?
Yes. Yes.
Okay. Yeah, I apologize. It's a little hard for me to see exactly. I see a little window here, and it looks like it's the same thing you guys are seeing. So
John, on the bottom left, if you press the third button over from the left, that should do it.
Yeah, well, that's what I've been pressing. That's exactly right. That's the full screen. And you're seeing something different, I think, right?
Okay, yeah.
I think this is a nuance of the Mac itself. Because when it perceives that you're sharing it, it shows something else than what you see. So it's a two-screen thing, and I think this is related to the Mac. So rather than try and figure it out, I'm going to just show you this slide here, if you can see it.
Fine.
Yeah, the Mac has they try and outsmart you a little bit, and in the process, I think they make it hard. Anyway, we're just going to do a brief intro to all this stuff, and if you guys have any questions along the way, Let's make this conversational. Stop me if I confuse you. Stop me for sure if I say something wrong. I'm going to try and just show you lots of pictures. And because I never quite know who I'm talking to, I haven't put in a lot of math here. I think I have a grand total of 1 equation in this whole thing. So we're going to try and do this all with pictures and hopefully have everybody come away with a little bit deeper understanding of what first-order optics is really all about. So let's see. So the question is, why is all this so hard? I mean, designing optical systems should be pretty easy. But the law of refraction is not that simple. The law of refraction, I said I had 1 equation, maybe there's 2 here. So I have the law of refraction, which is just given by this expression. Hopefully you can see my cursor there. It's just n2 sine theta 2 equals n1 sine theta 1. And that's the way we figure out where rays go when they intercept a surface. Rays refracted at a spherical surface don't all focus to the same point, and all you guys know this. I mean, I know I'm not telling you anything new here, but if we have a spherical surface and we have a ray coming in from the left, it comes down and it's going to intercept the axis at a different point than where a ray intercepts the axis starting from a different ray height. And we can go all the way down to what we call a paraxial ray, which is a ray that's nearly axial. It's right along the bottom, and that intercepts even further out. And so this turned out to be a big problem for a very long time. It's what I call a 100-year kind of problem. It took from the time people first started making optics until they really understood what they were doing. It took about 100 years to figure this simple stuff out that we're going to discuss in about an hour here. In 1841, it was Gauss, this German mathematician, astronomer guy, who published this treatise on optics where he demonstrated that as far as these rays very close to the axis are concerned, a lens of any degree of complexity could be replaced by just 2 principal points and 2 focal points. And the distance between these principal points to the respective focal points are the focal length of the lens. And we'll show you how that works in just a second. And this was really the first time ever that a formal mathematical definition of focal length had been established. I mean, we all think of focal length, we know what that is. But it took 100 years for people to figure this out, and it was Gauss who really came up with these rules that we're going to talk about. But before we do that, we've got to talk about a couple things. First is that first-order optics is slightly different than Gaussian optics. It turns out that, but only in the way that we get at it. They produce the same results, but first-order optics is really talks about the first term in what's called a power series expansion that solves for ray heights in the image plane. And I showed you those signs, you know, the law of refraction. It turns out you can do these expansions, these mathematical expansions. And because we talk about axially symmetric systems, these expansions only have odd terms. So in other words, aberration theory contains the first order term, which we're going to talk about tonight, and that's why we call it first order optics. But there are higher order terms called third, fifth, and seventh. And I know you guys have heard of this stuff, but it's because of an axially symmetric system that we have these odd order terms. Paraxial optics uses real rays. So we actually do this, the law of refraction exactly, and they follow the same basic rules as first order optics, which are the same as Gaussian optics. So all 3 of these are really the same thing. And when we talk about paraxial optics, the law of refraction becomes this little thing here, n2 over n1 is about equal to just the angles themselves. When things get really small, we don't have to worry about the signs anymore. And so this becomes really the optics of a perfect imaging system. So what do we mean by that? It means that well-corrected systems closely approximate Gaussian systems. So when we have our perfect astrograph, it is a Gaussian system. And these things are, this whole business of Gaussian optics and first-order optics is really super useful for things like laying out and understanding optical systems, both simple ones and super complicated ones. It allows you to determine image positions and sizes, and I see lots of questions on cloudy nights that relate mostly to Gaussian optics. There's a few advanced guys doing design and that sort of thing, but a lot of people ask very simple questions that can be answered by what we're going to talk about tonight. It also is useful for defining the aberrations, which are departures from Gaussian. In other words, Gaussian's perfect, whatever isn't Gaussian is an aberration. And ultimately, we can use these Gaussian properties to determine what are called aberration coefficients. So we can actually figure out what aberrations we have just even by knowing the first order properties. So we got to have a few rules, and I'm going to get into pictures because I don't like all these words. So we'll show you some pictures here in a minute. But one of the things we're going to do is we're going to assume this homogeneous media so that rays take a linear path. And you know that the atmosphere isn't very homogeneous. The atmosphere, the Earth is curved, and the air gets thinner as it moves into space. And rays from a star actually follow a curved path to get to our telescope. But if we take a really small chunk of that atmosphere, like sitting in front of our desk, we can assume that the air is pretty much the same and that rays take linear paths. We're also only going to discuss rotationally symmetric systems. In other words, systems that have an optical axis. We can do a lot of this stuff with off-axis systems, but that adds lots of complicating factors which we're going to ignore here. It's too much for 1 hour. And the other thing we're going to do is we're going to talk about rays and optics in what's called the meridional plane. And I'll show you a picture of that in a minute. And that plane includes the optical axis and the field points. And we'll talk about what that is in a minute. And any rays that go in the meridional plane are called meridional rays. And so that's where first order optics takes place. There are other rays called sagittal rays and skew rays, and we're going to ignore all that stuff because it adds a lot of complication to it. It's important for real optical design, but for just getting started and getting everybody on the same page, it's just a complicating factor that we're going to simplify tonight. And then lastly, I'm gonna let you guys in on a secret among optical engineers, and that is that light always travels from left to right. This is a law of the universe. Obviously, it's a convention, but it's very common. If you get interested in any of this stuff and you want to look it up, you'll open an optics book and you'll see immediately that light always goes from the left side of the page to the right side of the page, and that's because of the coordinate system. And I hope you guys can see that that picture, and I'll try and point out what this is. So basically, light travels from the left side of the screen along this axis that's called the z-axis to the right side of the screen. We're going to put an object over here in this xy plane somewhere, and we're going to pick a point on the y-axis, and we're going to image it along the red rays to the y-axis in the image plane, and that's what we call the meridional plane. Anything that's in the xz plane is called the sagittal plane, and you may see people talk about that, but again, that adds some complication that we really don't need to talk about. So we're going to start a little complicated here, but I'm going to make it much simpler. And we're only going to talk about rays that happen in the YZ plane. And any ray that starts out, say, up here at some XY location and ends up over here in some XY location in the image plane is called a skew ray. It just kind of goes flying through space. It doesn't worry about planes at all or the axis. And again, optical design programs will take care of skew rays without any trouble, but tonight we're not going to do that. Let's talk about these Gaussian cardinal points. And maybe you guys, maybe some of you guys know about these things. This looks like a really complicated diagram, but it's really pretty simple. What we have is and I've indicated here what we call a thick lens. It's just a lens sitting here in space. And Gauss defined the first thing called a principal plane. And the principal plane is found by sending a ray in from the left and looking at where it comes out on the right. And he made a very interesting observation. He said any ray that comes out on the right that originates from a ray that's from infinity on the left goes through the focal point. That's how we define the focal point. And we find the intersection of those two rays, which is labeled B here. That is the principal plane, and all refraction will appear to occur along that plane. We could find the opposite plane for rays coming in from the right side. So we go from C, we send a ray in parallel to the axis. It comes out somewhere, passes through the forward focal point, and we just project backwards to find point D, which is the other principal plane, the forward principal plane. So those principal planes are where refraction appears to occur. And we're going to use this to simplify optics tremendously. We also have the focal points are two of the other cardinal points that Gauss talked about, and there are two other ones that are a little bit more obtuse. These are called the nodal points, and the nodal points are points of unit magnification in the thick lens. So if we send in a ray at some angle u to strike this first nodal point, it'll come out at the exact same angle, okay, from wherever that nodal point is. And here, I've kind of indicated that the lens has two different indices on either side of the lens. So we're talking about an index here that might be air. We're talking about an index here that might be glass, say about 1.5, and here's water on this side. So you might think of this as a magnifying swim glass, and these are all the full nodal points. And this is just the definition of what I described here. But the thing I want you to note is that the nodal points and the principal points, which are these two things here, the N's and the P's here, they fall in the same place if the index on the left side is the same as the index on the right side. So if it's an air, we get rid of two of them right away. So we're down to just the principal points. The nodal points turn out to overlap the principal points if the lens is in air. And we get one other benefit if we're in air, the forward and the rear focal lengths. And again, the focal length is the distance from the principal plane to the focal point. These two lengths, f and f prime, become the same if we're in air. If we're not in air, they're different. So that's important. Now, we never put our telescopes underwater, so this is kind of an academic exercise for those of us interested in telescopes, but optically, that's the way it works. So we're going to start simplifying right away here. We're going to assume that all the optics are in air going forward. So how do we trace rays going through a thick lens? It's pretty straightforward. Gauss came up with these three rules, and it's very easy. We take an object point on one side, we send a ray in parallel to the axis on one side, and we know it emerges from this rear principal plane to pass through the focal point. We have another point that passes through the nodal point here, another ray rather. When it goes into the nodal point, it emerges at exactly the same angle that it went in at. Goes in at one angle, comes out at the same angle. And then we also know that any ray that goes through the forward focal point comes out parallel. So we can use this trick, these three rays, we can just simply draw them to figure out where does the image occur. So pretty simple. So how do we figure out one other thing that's maybe seems super simple but is important to understand is that there's a one-to-one relationship of object and image points. We call this a conjugate relationship, so that any point on the object relates to any point on the image. So rays that start out along the axis at the object point have to pass through the axis at the image point. Excuse me. So this is useful for just determining where the image lies and where the rays go.
John, we have one question.
Oh, go ahead.
Earlier you said this all refers to air, and Josh is asking, how about with oil-spaced lenses? Is that kind of what you're referring to?
Absolutely, yeah. An oil-spaced lens will have the same effect as having an index on the of the oil on the other side of the lens, and you can treat it. You know, it depends on how it's configured. I mean, sometimes oil is used as an actual optical element, but if it's just in oil, for example, a oil immersion microscope lens, then the nodal points don't sit on top of the principal plane. So that's actually a very good example.
Thank you.
So how do we handle multiple element lenses? This is one of the powerful things about what Gauss did, is we don't really care what's inside this box. I drew a lens earlier, but we don't really care. This could be 15 elements here, and we can reduce this entire optical system to just these principal points. That's the cool thing about this approach. So we could have a modern eyepiece here that might have 7 elements in here. We don't really care what they are. We can still use this whole technique that Gauss developed to find out where, given an object, where does the image fall and what's its orientation and what's the magnification. And in fact, we could have an entire telescope inside of here, and later on we're going to use that fact to solve for a Cassegrain telescope. And you'll see that it really doesn't matter what's in there. We can solve a lot of things just knowing this fact that Gaussian optics really don't care what's in there. What it cares about is where the principal planes are. How about we simplify even more? All these principal planes are pretty useful for doing system design with thick lenses. We don't normally need all of this stuff, particularly for most of the things we do with astronomical optics. And it turns out that we can shrink the lenses, and rather than having what we call thick lenses, we can have thin lenses. And in that case, the separation between the principal planes goes to 0, and we end up with a single principal plane and a single focal length. And we're going to be drawing that thin lens system as I've done here. There's going to be an object point somewhere out here. This could be at infinity. We'll come back to that in a minute. We're going to have a focal point, and these two focal lengths will be the same. Forward and back are the same in air. And we can just use this technique of drawing these 3 rays. We only really need 2 rays to find the image point. And sometimes it's convenient to remember all these rules because sometimes it's easier to use one ray rather than the other to calculate where the image lies. So as long as you got a ruler and a pencil, or better yet, AutoCAD, which is exactly, can give you numbers, very easy to draw these kinds of things and figure out where the object and image points are. Before we go on, I want to talk about spaces, because this is another thing that I sometimes see some confusion over in discussions on cloudy nights, is the different kinds of spaces. Well, the first thing we talk about is real space. This is where rays really exist. Okay, you can put a card there. You can see the light if it's in real space. So if you have a magnifying glass, which is a lens with positive power, and you take it out in the sunlight and you focus on a card, those are real rays in real space burning a hole in the card. Virtual space is space where the rays appear to exist. They don't really exist there. This is space where you can't really put a card there. And the classic example is the reflection, your reflection in a plane mirror. And here's what a plane mirror looks like. The law of reflection says that the angle of incidence is equal to the angle of reflection. If we put our object here and we send rays out from that, they'll all bounce off the mirror and make it appear as if the image is sitting off on the other side of the mirror. We all know there's nothing there. You can't put a card there, but that's what we call virtual space. The other kind of space we talk about is object space. This is where the object is placed, even if it's at infinity or sometimes in virtual space. So the object could be real, it could be virtual, but this is wherever the object is, and likewise the image space is where the image winds up, again, either in real or virtual space or at infinity. And so a lot of times when I'm talking, I'll be talking about object space or image space. That's all you got to remember. That's just where the objects and images are located. So how do we use this whole business here of graphical ray tracing to handle multiple element systems? So I thought we'd just do kind of a quick example here to show you what, maybe I can make this just a little bigger because I know this is, hopefully that's a little bigger. This might be a little bit confusing, so we'll design a telephoto lens. A telephoto lens typically has basically a positive element and a negative element. And the object is at infinity, so we take our first rule, we send in, and we trace just the first lens. So we send in a ray from infinity. We know it has some field angle. We form a real image. That's really simple stuff. Now we're going to take and we're going to put in a negative lens, and we know the negative lens is going to go right there, and we use this real image as a virtual image now. And we know if we send in a parallel beam to strike that virtual object, rather, I said image, as virtual object, we know that that will pass through the forward focal point, and the light that's aimed at the rear focal point will be collimated. Collimated in optical engineering terms means to be rendered parallel. And so that ray will be parallel, and so we'll form a real image of that virtual object in back of the lens. And if we put that all together, we can trace a two-element lens. And we're going to do this a number of times through here. And this is kind of a fun exercise if you've never done it, to just trace out a lens like this. And it's really pretty darned easy. And here you get the location of the image, and you get the size of the image out of this 2-element lens. And you could do this for 10 elements if you had the patience for it. Of course, if you don't have the patience for all that, there is one equation. I said there's one equation we need to talk about, and this is one of my top 10 optics equations. There are a lot of really good ones, but this one's really up there. And this is a way to solve for the focal length of a lens knowing the object distance and the image distance. So if we just simply take a lens and we put an object at some distance and we measure how far it is in front of the lens and we measure how far the image occurs behind the lens, by using this relationship, 1 over the image distance plus 1 over the object distance, we find 1 over the focal length. And that turns out to be super useful for a lot of things. The one thing that's a little tough about this equation is we need to get the sign convention right, and it's actually pretty easy to remember. The image distance is always positive if the image is real and falls on the right side. It's negative if it's virtual and falls on the left side. The object distance is positive if the object is real and falls on the left side, and it's negative if the object is virtual and falls on the right side. And that sounds probably a little confusing if you haven't seen that convention before, but it's super easy to remember because remember, light always goes from left to right. We always start with the object on the left side, image on the right side, and in this configuration, everything is positive and we can solve for focal lengths. And this turns out to be really useful for solving for secondary mirror curvatures and some other things. And I want you to remember this because we're going to talk about this in a little while. This is a really complicated looking slide, but is pretty simple, and I love plotting things. And this is a plot of the thin lens equation showing the object distance, the relationship of the object distance as a fraction of the focal length to the image distance as a fraction of the focal length. And you can kind of see how this equation drives the object and image position. Up in this quadrant is where we have a real object and a real image. And one particularly interesting point is what we call a 4F system. It's wherever the object is 2 times the focal length away, the image will fall 2 times the focal length away, and so the total length distance between the object and image is 4 times the focal length. That's kind of a famous system, and the magnification will be -1, so the image will be inverted. Down here, we have positive magnification, so the image is upright, but we have a real object and a virtual image. So the object is very close to the lens. It's inside the focal length. And the lens forms a virtual image that's upright back closer to the focal point. In this quadrant, we have positive magnification, and we have a virtual object and a real image. So here we've got an object that's being formed by something else, another lens, and it forms a real image out further closer to the rear focal point, and that's a little bit like what we had with the negative lens in the telephoto lens example. Along these lines, this is where we have the image at the focal point or the object at the focal point, and one sort of degenerate case is right in the middle. This is where the object and the image fall right on the lens. You bring it so close to the lens that the object and the image kind of happen in exactly the same place. They overlap each other. So this is kind of a fun thing to look at. I don't know if it's particularly useful for designing anything, but it kind of parses out how the thin lens equation works and what it's telling you. So we mentioned optical magnification, and let's talk about that for a minute. And we're going to talk about what we call finite conjugates here. In other words, nothing's at infinity. And again, this is just our classic example where we have the object with some height here. It gets imaged using our little rules to some image here, and it has a height h prime. And the magnification is just equal to the ratio of the image height to the object height. Pretty simple. But it's also easy to show, and you guys can show it now using the thin lens equation, that the magnification is also equal to the ratio of the image distance to the object distance. And that turns out to be very useful for a lot of things. So you carry that around in your head. And the last thing is that the magnification is the ratio of the input angle from this image point out to the lens from this object point out to the lens back down to the image, and that's the ratio of those two angles. these are good things to remember. You can derive these pretty easily just from simple geometry. I'm not going to do it for you, but it's super easy to show that. But it's also a good thing to carry around in the back of your hip pocket for sometimes when you need to calculate quickly a magnification and you don't know exactly, you can't do this this drawing, but you can sometimes calculate it very quickly. And by the way, this kind of system here, we call this a focal system because we're dealing with an object and an image at finite locations. When we go to a telescope that we look through with an eyepiece, for example, we're looking at infinite conjugates, and we call this an afocal system because there's an object at infinity and the image is at infinity. And this is a Keplarian telescope, and this is the same kind of telescope we all use, whether it's a Schmidt-Cassegrain or a refractor, and we put an eyepiece on it. The way the magnification works in an afocal system is the afocal system magnifies the angles. So the magnification is the ratio of the angle out to the angle in, and that's how we find optical magnification in an afocal system. And we'll get to pupils in just a minute, and we'll talk about that as well. So speaking of pupils, let's talk about some special apertures that we have through the system. The first one and the most important one is called the aperture stop. And the stop is the aperture that limits the maximum diameter of a bundle of on-axis rays that radiate from an on-axis object point. Now I happen to have picked an example here where the object is all the way at infinity, so it radiates parallel rays. And in some sense that's almost the easiest thing because we put a stop in here, and a stop is physically just a hole in a card. That's all it is. It could be a fancy iris, it could be a thin film hole in a card, a thin film coating on a surface, but it's just a hole, and that's what admits light to the lens, and that's the aperture stop. Okay, so this is just a simple, very, very simple example. In telescopes, the stop, we'll talk about that real briefly. A Newtonian has the stop at the primary mirror. Simple refractor, same thing. The stop is at the front surface of the lens. And that's certainly true for almost, I think, all achromatic and apochromatic lens objectives and commercial telescopes and astrographs. They usually put it right at the first surface. It would be rare to have the lens get smaller in the middle, but that could happen. A pure Schmidt camera has the stop located at the radius of curvature of the primary mirror. Now, the Schmidt camera, nobody uses them anymore because the focal plane is curved, but that's what makes the Schmidt camera so big, is that there's an aperture out at the radius of curvature of the primary mirror. It's way in front. A Schmidt-Cassegrain telescope typically has the stop located at the front corrector surface. It's not at the primary. And that's certainly true for all Celestron Schmidt-Cassegrain telescopes. I think it's true for the Meads too, but I haven't checked those. And this is different than a classical Cassegrain where the stop is at the primary mirror. So it's a little bit different. Not hugely. Let's just to mention vignetting here. I think everybody talks about vignetting. I think most of you guys know what it is. But basically, we just take our example. If there's some limiting aperture back in the telescope that's too small, it will limit the off-axis rays. So this aperture, by the way, could be doesn't have to be an aperture. It could be a fold mirror, for example. If it's not big enough and it cuts off some of the rays, it'll block some of the off-axis light. And we'll come back to determining the minimum size for apertures anywhere in the system to prevent vignetting, but we want to make sure we're really clear we understand what vignetting is. It's whenever an aperture is cutting off some off-axis rays and causing light fall off. And I had to put a little side note in here because I see notes all the time where people say, oh, it got dimmer off the edge of my field and therefore it's got to be vignetting. That's not always true. There's really two reasons that light can fall off in the image plane of your telescope, say on your sensor. One of them is vignetting, and we just said that's due to physical obstructions in the image train. I also want to point out that vignetting is sometimes intentionally done to obstruct off-axis rays to control aberrations, and this is often done in commercial camera lenses. And back in the old days of film, you could open up the back of your camera and put your eyeball up near the corner of the where the film goes, and you could look back through your lens, and you could see that they vignetted lots and lots of space off to the edges of the field in a lot of lenses, and they did that to control rays that were that weren't good, that weren't going where they wanted them to go. But in general, unintentional vignetting is normally considered kind of a bad thing, so you don't want to see that. The second reason that light falls off is something called radiometric light fall off, and it's due to illumination effects that vary as cosine to the fourth in the image plane. And I'm not going to go into all the reasons. This isn't a tremendously complicated thing, but it's kind of off subject. But all optical systems suffer from this effect. So if you have zero vignetting in your system, you will still have a system that gets dimmer toward the edges. There's basically nothing you can do about it, short of putting in like some kind of gradient filter or something to control that. I mean, just physics causes this. And it's not the same thing as vignetting, so you want to be careful not to call that vignetting, or people will wonder what you're talking about. And, you know, I'm not going to discuss variations in transmission, which are stray light, which can also cause uneven illumination. So there are other things that can cause uneven illumination, but these are the two biggies, vignetting and radiometric light fall off.
John, can I ask a quick question?
Sure, absolutely. Just interrupt me anytime.
All right, that's interesting. Radiometric light fall off versus vignetting. I would probably assume, and correct me if I'm wrong, that probably we're almost always talking about radiometric light fall off instead of vignetting for SCT guys, or I mean, are we all using the wrong term?
Well, it may be. It depends a little bit. The edge systems, for example, are designed to cover a 42 millimeter field, but that's not completely unvignetted, as I recall. There may be a little bit of vignetting there. There may be some baffling issues there that cause the light to vary a little bit across the field. But typically, if there's no aperture blocking anything, then you're right. It's radiometric fall off. It's not vignetting.
Okay.
Yeah.
Yeah. Actually, now that I think about it, I think with my focal reducer, that could be true vignetting because there could be an aperture stop in there.
That's almost certainly the case. Focal reducers are a great example of where you do start to get a lot of actual physical vignetting.
Okay, thank you.
Yeah. So let's talk about the entrance pupil. The entrance pupil is the image of the stop in object space. Now we said the stop is a physical thing. And I actually have this lens sitting right in front of me. This is a cool lens that I picked up out of a junk bin someplace. And it's got a glass surface inside, and they did a thin film coating to create the physical stop. So it's a very colorful looking stop. It's actually a very cool lens. I think it must have come out of a copier or something. But if you look back through the lens at the front end, what you're looking at is the image of that stop. So in a telescope, that's sort of super simple. So a Newtonian, you look in the front, you see the mirror. Well, the mirror is the stop, and that is also the entrance pupil, okay, because there's no optics in between. But there are other systems, and we'll talk about them in just a minute, that's not true, where there's some optics in front. And what you're seeing is that hole that you see is really not the stop, it's the entrance pupil. And remember, because it's an image, it can be real or it can be virtual. In the case of, say, a Newtonian telescope, when you see the primary mirror, it is that's a real image that you're seeing. I mean, it's the real thing. So that's a real entrance pupil. And here's, in our little super simple case here, here's our lens, and here's the aperture, and in the front, the aperture forms the stop and the entrance pupil. So that's dirt simple. But we have other cases here. So here I've drawn another system, and this looks terribly complicated. Don't let this scare you too much. This is a system with a virtual entrance pupil. So we have a lens, and we have an entrance pupil. I'm sorry, we have a stop behind the lens. And this is a case where it gets a little bit confusing because now you've got to image this stop through the lens. When you look from object space here back through the lens, you're going to see a hole, but you're not going to see the stop itself. You're going to see an image of the stop, and the image of the stop is going to be virtual, and it's going to be bigger than the stop itself. And these rays, by the way, are just the rays I used to construct the location. It's a little hard to see. It's the green line there. Hopefully you can see that for the entrance pupil, which is virtual. So in this case, the entrance pupil is larger than the stop. And again, most common telescopes that we're dealing with have a real entrance pupil on top of the stop at the first surface, which is a lens or a mirror or whatever. Most telescopes are of that type. Although, let's see, yeah, Maksudov probably has the stop right at the first surface, so that may not be a good example. So how do we define focal ratio? We're all familiar with this idea that the f number is equal to f over d, where f is the focal length and d is the diameter of the objective. Well, that's dirt simple. But that's really only true for a simple telescope with a stop and an entrance pupil at the first surface of the system with a single component. So, for example, a Newtonian telescope, that's how you calculate the focal ratio. F number is actually f over d, where f is the effective focal length, which is the distance from the principal plane to the focal point, and d is the diameter of the entrance pupil. Okay, so it's important to know that it may not be the same as just dividing the diameter of the stop into the focal length. And it's also only true when we have the object at infinity. And optics guys have to talk about objects anywhere, not just at infinity. We don't just talk about stars. So when we talk about things that are close up, we typically don't talk so much about f number anymore. We talk about something called numerical aperture, but I'm not going to get into that. You guys probably have heard of that, but
hey, John, I have a question for you.
Yeah, sure.
So when you're talking about RCs that have giant obstructions, they still give you a focal ratio, which is essentially the focal length divided by the diameter, right? But
that's correct.
But how is it that fast, even though you're losing that much light from the aperture of the scope?
Right. Yeah. So the obstruction in that case really doesn't come into what the optical speed of the system is. It does come into play with how much light are you getting through the system. It also affects the size of the diffracted star image. Okay, the image will change shape because of that obstruction, but it doesn't change the fundamental focal ratio of the system to have that obstruction there.
Okay.
And again, it's simple when you have one lens, but it's not always so simple. What if we go back to our little telephoto lens? And by the way, this is not a zoom lens; it's just a telephoto lens. And people love telephoto lenses because this is how you get such a short package out of something you buy, say from Canon. Is they just put basically lens groups together that look just like this. And so if we have a stop in the system, and we ray trace it backwards using all of our little tricks, we find out that we have an entrance pupil that's virtual here. Well, how do we find the f number here? Well, we take and we project. First of all, we go from the image point out to the principal plane. Okay, and the principal plane here, remember, we send in a beam of light from infinity, and wherever it comes out, okay, we trace it backwards to find where our principal plane is, and that forms the effective focal length. And I just called it f because that's the way we wrote the formula. But remember, this f here is the effective focal length of this combination. And how about the diameter? Well, we don't use the diameter of the stop here. We use the diameter of the entrance pupil because that's what projects out onto the diameter of the principal plane. So, how do you know what the focal length of your camera lens is? Well, you got to look at what's printed on the side. Because they know how big the entrance pupil is and they know what the effective focal length is. And you can read the effective focal length on there as well. You could set up with a laser to measure all this stuff, but holy smokes, that'd be kind of hard. But the point is, it's not immediately obvious when you pick up a telephoto lens, how do I calculate the focal ratio from what I am holding here? And to do that, you've got to send a laser through and maybe have an optical bench and figure out all these points and calculate it. So it's not so easy, and that's why they print it on the side of the lens. And then the really important one is the exit pupil. Well, the exit pupil, just like the entrance pupil, it's an image, and it's the image of the stop. Remember, the stop's physical, but the pupil itself is the image of the stop back in image space. So if you put your eye behind your system and look forward through it, the image you see of the stop is the exit pupil. And again, I just turn this lens around, and there it is. There's what I see. That's what the exit pupil looks like. And this gets really interesting when you have multiple mirror systems like a Schmidt-Cassegrain. We'll talk about that. That's coming up. In an afocal system, like a telescope with an eyepiece, the exit pupil is called the Ramsden disk, and it's named after this guy Ramsden who kind of discovered it. There's kind of a story about that. You'll have to look it up because I don't quite remember what it is, but I always just call it the exit pupil, but astronomers love calling it the Ramsden disk after that guy. And remember, the exit pupil is an image. So it can be real or it can be virtual. It can sit, and I'm going to show you examples of both here in just a second. And the exit pupil, from a lot of the discussions that you've seen on cloudy nights, the exit pupil can be very important in terms of calculating a lot of parameters about the system. And I didn't want to go into all that level of detail, so we're not going to go into all that stuff. But there are some nice things that that are important about the exit pupil. But let's look at a couple of examples here of this thing. And these are kind of fun. These are afocal telescopes, because that's what we like to use when we have an eyepiece. I mean, we're all imagers, so I don't know. I think last night was the first night I had an eyepiece on my telescope in what, a year and a half maybe. I almost never do it. But for the guys who are looking through them, we have a Keplarian telescope, and I've sent 2 bundles of rays in here at kind of both extents of the field, so that you can see what's going on here. The rays come through, and they are limited by something we call the field stop. This is what limits the angle of view of the telescope. Then we go through the eyepiece lens, and the eyepiece lens re-images this image plane back to infinity. And so the output of an afocal telescope is an image at infinity. So when you put your eye here, you focus your eye at infinity to see the image. And the image of the stop, in this case, which is the objective lens, is formed by the eyepiece lens, and that forms the exit pupil right here, and I've shown that in blue. And this is where you want your eye to go, because your eye should be the diameter of these little blue ticks here. That's the diameter. If that diameter is smaller than your eye, life is good. If that diameter gets to be bigger than your eye, then life is bad, because now the stop is no longer located up here at the objective. It moves down here to your eyeball, and that causes all kinds of problems. Not the least of which is that you're not using all the aperture that you thought you were, that you paid for. So you don't want to get too big of an exit pupil here. But in this case, we've got a real entrance pupil, a real exit pupil, and a real field stop. We go to a Galilean telescope, and these are crummy little telescopes usually that we use for opera glasses usually. We have an objective lens, and we have a negative eyepiece lens. So this has a negative power. And when we do that, we discover that, yeah, we get, the rays are re-imaged to infinity, but now the exit pupil becomes virtual, and it sits in virtual space here in between the 2 elements, and the rays diverge from that virtual exit pupil, and now you got to get your eyeball right up against this lens to grab as many of these rays as you can. And the problem is if it's high power, you can't grab all those rays, and it really messes up your field of view. And so these are typically very low power to keep these ray angles tiny so that you can get all those rays into your eyeball. But this is an example of a real image pupil with a virtual exit pupil and a virtual field stop. And these things are really hard to look through if you've ever done. I'm sure we've all done that. For the telephoto lens, again, you can do this exercise. I love the telephoto lens for what's coming up here, but basically I showed all the construct images here, and we won't take time to reconstruct this, but the exit pupil lies in between the two elements here. And what I really like about the telephoto lens is the equivalent reflecting version, which is a Cassegrain telescope. A Cassegrain telescope is simply a reflecting version of a telephoto lens. And so in this case, we have the rays coming in from infinity, and again, I've drawn the 2 rays, the red and the blue, are off at the extremes of the field, which in this case I picked 3 degrees just so you could see it. The rays come through. Again, they're trying to focus over here initially at the prime focus, but we can find the location of that principal plane here, and we can calculate what the field angle is and calculate what the image size is. And when you do this, you can work out also where the exit pupil is. And if you take your camera off the back of your Celestron and look in, you will see a little distant image of the primary. And that little distant image of the primary is the exit pupil for the telescope. Okay, so that's what you're looking at when you look in there and you see that image back in there. It's just an image through the secondary. All this, all these rays. I mean, I love all these rays. They make pretty pictures, but they're complicated, and I think it makes understanding a system very hard. So optical engineers almost never do what I've shown you in all these slides. We usually use just 2 rays called the marginal and chief rays. And these 2 rays make understanding an optical system really easy. So we're going to simplify all this. The marginal ray is going to be a ray. There's an infinite number of them, but we're going to pick one of those infinite number of rays that starts at the on-axis image point, and it touches the edge of the stop, and it passes through the on-axis image point, and it defines the outer edge of a bundle of on-axis rays. And I'll show you what that looks like in just a second. The chief ray is sometimes called the principal ray as well. I don't see that so much. Most people talk about the chief ray, but it is also called the principal ray somewhere, occasionally. And it's a ray at the maximum field angle or extent of the object in object space, and it passes through the center of all the stops and all the pupils, and it just touches the edge of the field in the image plane, and it defines the center of a bundle of rays at the maximum field angle. Well, all those words are kind of confusing. Let's look at a picture. So here are the two rays, and here's our simple example of a lens. It's a symmetric lens. We have an object, and our object, of course, we love arrows in optics, so we got an arrow. We start with the object point here, and the red ray is the marginal ray. It clips the very tip of the edge of the lens, and it goes back down to the image point. That is the marginal ray. The chief ray is a ray that defines the edge of the field of view, and it just goes through the center of the stop, and it ends up at the tip of the image. So it defines the maximum angle. Ray heights everywhere are measured in, remember, always Y, and chief ray. And so, if you ever look this up in an optics book, you're going to see that the marginal rays are all designated as having Y heights and U angles. This is a typical convention. All of the chief rays always have a Y bar height and a U bar height angle. So chief rays are the ones with the bars over them. So if you pick up Optical Engineering by Warren Smith, or even a lot of the telescope books, they'll use the same notation. One of the cool things that you can do with this is, now that we understand what those rays are, we could actually do something called a telecentric imaging system, and this is kind of a magical thing. I love this. What we do is we take our lens and we put our stop right over the focal point. So what does that do? Well, that defines, remember, our chief ray starts at the outer edge of the field, goes through the center of the stop, and now it hits the lens and it becomes collimated. It's collimated light. So what does that do for you? Well, if we have to put a sensor here and we want to focus on this object, when we focus by moving our sensor back and forth, it doesn't change height because the chief ray is parallel to the axis. So the image can go in and out of focus and it doesn't change size. And this is a really common trick. A telecentric imaging system is a very common trick for measuring the size of things, say on a production line or something, where you want to know, is something the same size? You want to be able to focus without changing the size of the object. So it's very good for measuring the size of things. Let's look at how these rays, what they look like in a Keplarian telescope. Again, it's like all our telescopes. The marginal ray in red goes through the objective lens. It goes through the image plane, which has a field stop. Okay, the chief ray comes in and its angle defined by the edge of the field stop, goes through the eyepiece lens, passes through the exit pupil. Wherever the chief ray, remember, wherever the chief ray touches the axis, there's either a stop or a pupil there. Here it's both the stop, it's the entrance pupil and the stop, and here it touches the axis at the exit pupil. The marginal ray, okay, touches the axis wherever there's an image. So the image happens right where the field stop is, and then it gets collimated. So the image sits out at infinity here. Okay, so the field stop in a Keplarian telescope, this thing right here, is what defines the field of view of the whole telescope. The apparent field of view is determined by how big the eyepiece makes the field stop appear. So in angle. So when you put your eyeball up here at the exit pupil and you look in, you want to see this thing subtend a great big angle. So typically they make this very big, and this focal length, they have to make it kind of small. And there's some other tricks that they use to do that. But the field of view is related to the apparent field of view through the magnification of the system. So if you have let's just say you had an apparent field of view of 100 degrees and you were operating at a magnification of 100, you'd have a full degree of field out here in object space. So this angle of this blue ray would be 1 degree for that situation. So remember, this is an afocal system. That's the way it works. We've got parallel rays coming in, parallel rays coming out. How does a Cassegrain telescope look with the same thing? Again, it's really simplifies things. We've got one ray that comes in, it bounces to the secondary, it bounces down to the image plane. The chief ray, which remember is at the edge of the field, comes in, bounces off the secondary and up to the image plane. Well, how do we find where all these go? Well, remember, all we got to do is find the principal plane here off the effective focal length from wherever this focus position is. The ray will just come down, and that's the ray that is the edge of the marginal ray. And it's the same as if it were coming from this imaginary thing that Gauss invented way back when. And it makes it very easy to understand complicated systems like this. So the thing to remember about these rays is the chief ray defines the center of the bundle of rays at the maximum field angle. And to prevent ray vignetting, and this is the really interesting thing, well, actually, let me finish that statement. The chief ray defines the center of a bundle of rays at the maximum field angle, and the diameter of that bundle of rays is defined by the marginal ray. So in order to prevent vignetting, and this is a big important takeaway, the radius of any aperture in the system has to be at least equal to the sum of those two ray heights anywhere in the system to get all the rays through. And I see this question come up all the time on cloudy nights. How do I calculate the size of my minor axis or of my secondary, my Newtonian? Well, this is how you do it. If you want zero vignetting, you calculate what's your ray heights for the chief ray and for the marginal ray and add them together. It's super easy. And you can do this for the secondary size in your Cassegrain. You can do this for any lens you need to put into your imaging system. As long as you can figure out what the field size is and what the ray heights are, you can figure out how big of a hole you need or mirror you need. You do have to be careful. No aperture can have a radius smaller than y. Remember, that's the marginal ray height. Or it becomes a system stop. So that's you don't ever want that to become too small. And I see guys every once in a while saying, gee, I made my Newtonian so much better by putting this dinky little tiny secondary in it. And what they're doing is they're not using the full diameter of the telescope. They've made it a much slower system. So they get totally different imaging characteristics out of it. And just a takeaway, remember the pupil exists wherever the y bar height is 0, and an image plane exists wherever y is equal to 0. So, and also don't forget, and I've gotten into some discussions with guys on cloudy nights about this, that the chief ray and the marginal ray can exist in either real or virtual space, sometimes both. So you have to be a little careful. It depends on where you are. But you need to understand that they can be real or not real. I've told you enough now. If you guys followed me, and I haven't put you all to sleep by now, you've got enough information to completely design an optical system. This is the cool thing about all this stuff. If you dig through it, this is pretty simple. And we can design a Cassegrain system. We're going to do it in like 2 minutes here because I know we're running out of time. So if we set up a Cassegrain, we can compute the first order properties. I love 14-inch telescopes, so forgive me. 14-inch telescope, we're going to make it an f2, f8 Cassegrain to cover a 42-millimeter circle at f8. So the system magnification is 4. That's just 8 divided by 2. The focal length of the primary is f2, so it's going to be 28 inches. And the effective focal length is going to be f8 times 14. It's going to be 112 inches. And the half field angle, we can just calculate that. Again, remember, that goes all the way out to the principal plane. So we know that the half field angle height is going to be 21 millimeters, half of the image circle, divided by the full effective focal length. So that tells you that out in image space, we're going to have a half field of 25.4 arc minutes. And we need to pick a back working distance for our Cassegrain. This is an arbitrary number. For small telescopes, it's typically the diameter of the mirror, so that's going to be 14 inches. And the way we do this is really easy. Basically, we just draw first the primary mirror. We then offset the principal plane out by, stop. We start with the primary mirror. We move back to the principal focus, and then we put a principal plane that's 112 millimeters out in front. And now we just start drawing rays. And just like I've shown you, we take a parallel ray in, and it goes down to the primary focus. We also know that out here at the principal plane, the ray coming out the back of the telescope has to look like it came from the edge of the principal plane and focuses at the focus. And so the intersection of intersection of those two right there happens to be where the secondary goes. Super easy. We also know there's a virtual object there, and the image is there. We could use the thin lens equation to calculate what the focal length of this is. That would be an easy way to do it. In fact, that's a nice way to do that. And you know that the radius is just twice the focal length. So we get the radius of curvature. We get the we also get the diameter of the mirror, because remember, the diameter of the mirror has to be equal to the height of this blue line plus the height of the red line. So that gives you the radius right there. The same with the hole in the mirror. Now the hole in the mirror can be pretty big, but the minimum size is just the sum of the chief ray and the marginal ray. That gets all the light through, guaranteed. So in one fell swoop, I think it took me 10 minutes to work out all of the Cassegrain stuff here, and you don't need a single formula. If you can just draw it, you can calculate everything you need to tell a guy how to make a Cassegrain telescope. So it's super easy once you understand the first order properties. You know, we've really just touched on some basic stuff. Hopefully I haven't put you guys completely to sleep. I know I'm talking fast because there's a lot of stuff here. And I'm sure you guys know a lot of this stuff, but this at least gets us maybe on the same level in terms of talking about you know, the terminology and that sort of stuff. And you know, there's whole books written on this stuff that include ray tracing, Lensmaker's formula, optical invariant, Fermat's principle, baffling, all kinds of stuff that you can do with this first order stuff. And the more you know about this, the easier it is to calculate little things like, you know, what spacing do I need for my focal reducer in order to get a magnification of 0.63? It's super easy. So there's a lot you can do with this stuff if you look at it. And again, I would say for amateur astronomers, myself included, I would say 90% of what you really need to do for setting up your telescope is what we've talked about in the last hour. It's super easy. So that's really what I had to say about first order optics. I hope you guys learned something, and I didn't put you all to sleep. Any questions?
That was a great presentation. Thank you, John. Yeah, guys out there in the YouTube side, remember you can type your questions right into Q&A. And guys in the room, feel free to ask away.
I've got a quick question. So going back to the beginning of the presentation when we're talking about the different, I guess they were referred to as focal points. So we're talking about the principal points, the nodal points, if I remember correctly. So one of the things that I found particularly interesting is between the two nodal points itself. Now, I may frame this question incorrectly, but basically the nodal point is that if I were to point a beam of light at one of the nodal points, we can make the safe, I guess, assumption that the nodal point would exit. So the light ray would exit at the secondary nodal point at the same angle at which it entered, correct?
Perfect, perfect. You said it perfect. Yes.
Okay, so the question that I have is then, so I'm looking at the distances there that are in between those two nodal points. Now, is that consistent across the different mediums that exist? So if I were to measure, say, the nodal points in between, or sorry, the nodal points that exist, say, in glass, are they the same as they would, say, in air or a diamond or a sapphire?
Oh, yeah. No. The position of the nodal points will depend on the thickness of the system. It'll depend on the refractive index of the system. So, for example, if it was made of diamond, it would be diamond has a very, very high index compared to, say, glass. So the nodal points will exist at different positions. And in fact, one of the sort of first-year graduate labs that you take in optics is to actually measure the nodal points, and it's done on something called a nodal slide. And it's where you mount they usually hand you a great big thick lens made out of glass, and you put it on this thing, and the thing can rotate about any point, and you can actually move the glass backward and forward over that rotation point, and you use a microscope to look at the point where you can rotate the lens and the image doesn't move anymore. And that's the location, that's when you found, when you're focused on the nodal point itself.
Oh, that is really cool.
Yeah, so think about that. So you know, here I've said, well, we shoot the ray, this red ray in, and it exits at here. But what that implies is that if we were to rotate this thing about that nodal point, that this thing will just translate. It won't actually change angle. So we could grab a hold of this lens and rotate it around within some limit. I mean, you can't go all the way around, obviously. But if you rotate it, say, plus or minus 10, 15 degrees, that the ray coming out the backside isn't going to move, isn't going to change angle. So if you're looking at this with a telescope, if you set everything up just right and you rotate this, nothing will move.
That is so neat.
Yeah, it's kind of a cool thing, and that's what a nodal slide is used for.
Awesome. So then I guess the next question would be, and this is, I know the answer, but I would just rather have the verification from you. So is the wavelength of light, well, dependent upon the wavelength of light that is being passed to the nodal point, that will also affect the angle at which it enters and, sorry, exits? Would that be right? Or is it just entirely dependent upon the angle that I position that particular wavelength of light at that nodal point?
Yeah, you've brought up a really, really good point. And I should have mentioned that as one of our rules. We're really only talking about using one wavelength here. Okay. Because, as you know, glass has dispersion, meaning that the wavelength of, the index of the glass changes with wavelength. And so the nodal points will indeed be wavelength dependent. And that's a really good point, and I'm really happy you brought that up. But here we're kind of assuming that we're, for example, illuminating this with a laser. Okay, so it's just one wavelength. And then it gets easy. It's kind of a blurry mess if you use white light, because then it doesn't quite work perfectly. But it actually works. It works well enough. I think back when I did it in my first year of graduate lab, I think we did it with white light, as I remember, and it works pretty well.
So then when you guys are working in your labs, is there a particular wavelength of light that you would use that provides you with, say, the most consistent results?
Oh, everybody uses 6328 is the helium neon laser wavelength. Everybody uses that for almost everything. And you almost have to stop and think, oh, wait, I'm using some different wavelength. So it's very easy to get trapped into thinking just about one wavelength all the time. And you'll see me making mistakes on cloudy nights every once in a while. I forget, oh, yeah, I better mention that this is monochromatic. But you're right. It's very important to think about the wavelength effects.
That is so neat. Thanks a lot, John. Appreciate it.
Good. Yeah, no, hey, it's my pleasure. Okay, now that should show me again. Is that right?
Now we see you, yes.
There we go.
Yeah, we can see your face.
So you shoot with a 14-inch Edge HD, right?
I do. Yeah, I have a 14-inch Edge HD. I've got a IFI on-axis guider, which I love, and I image with a 6D.
Yep. So do SCTs deserve the panning they get?
Not at all, actually. You know, I've actually taken and measured some of this stuff on a 4D interferometer, but I haven't done a full system test. But I'm about to do that, and I've been doing some other testing I can't talk about. But the SCTs that I know Celestron are producing right now are actually pretty good optically. So I've been impressed. Now, again, I guess I'll hold off making too bold of a statement because I haven't put it on an interferometer yet, but I suspect they're pretty good.
Yeah, I have an Edge 800, HD 800, and I like it.
Yeah, they're really super telescopes. I think the biggest problem with them is just sort of thermal control, just making sure that you get rid of all of the air currents and all that stuff. But once you get it stabilized, they're very good. The field performance is outstanding. The mechanical stability needs a little bit of work, but mostly optically, I think it's a pretty good design.
And the price per inch of aperture, hard to beat for something that you can really image with. That's
absolutely right. I mean, for what they are, they're cheap for what they are.
Yep.
So I've got another question just regarding the f-stop.
Sure.
So we have the ability to use mechanical field stops, and that is an accurate statement, correct? So the focal reducer itself will act as a stop itself?
Well, yeah, actually the focal reducer does not act as a stop. The focal reducer merely re-images the light going through it.
Yes, yeah, so my question, I'm sorry, I framed the question incorrectly. But does it have properties that act as a stop within it? Or how can I... I apologize. I just lost the question completely.
No, that's okay.
I wanted to frame it up.
Yeah,
I'm just not articulating it.
Yeah, let me just tell you, in essence, a focal reducer is simply a positive lens at the output. That's all it is.
Mm-hmm.
And we didn't talk about the optical invariant, but when you increase the focal ratio, you conversely change the field. Okay, the field gets bigger, but you end up with issues with baffling and all kinds of things. Now, Celestron's designed their focal reducer to handle a lot of that stuff, but you still get a lot more vignetting out of the focal reducer. And I haven't looked at the stray light. I'm not quite sure how it's baffled for that. But you do have to be a little careful with focal reducers that you get good image quality and you get enough illumination over the field.
Gotcha.
And do you know where the field stop is in that system when you put your camera on a focal reducer? Where's the field stop? I'll throw a quiz back at you.
Yeah, no, and I think that's where my question was leading to. I was trying to understand is the location of the field stop, or what is that field stop composed of? Is it something that is mechanical, or is it something that is virtual, such as
mechanical? And it's so obvious when I tell you, you're going to say, "Oh, geez, yeah, I should have realized that." It's the edge of your camera sensor, is the field stop. So that's what determines your field size. So if you want to know how many degrees do you see out in space, what you're going to do is you're going to take, let's just say, for example, that you're at 21 millimeters. I mean, that's the number Celestron throws out. And on my C14, the focal length, the effective focal length, is 3,911 millimeters. So all I've got to do is take that 21 millimeters to find the half angle, 21 millimeters, and divide it by the 3,911 millimeter length to get the arctangent of the angle. I'm sorry, to get the tangent of the angle. Then I take the arctangent to get the angle of the field out in object space. Does that make sense?
Yes, it does. It makes absolute perfect sense.
Okay.
It does.
Yeah.
So it almost seems like you're going back to using magnification, or coming up with the ability to use magnification when it comes to imaging, right? Because you're measuring the angles. I think you almost touched on that.
Well, let's go back. You know, it's that whole business I talked about with early in the talk, where I said, you know, we don't care what's in this box. It could be a whole lot of components. It could be a little lens. It could be anything. Well, in this case, what's in that box is the whole Schmidt-Cassegrain telescope. Okay, that's what's in there. And so we don't really care about the mirrors or the focal lengths or anything. To first order, all we care about is the effective focal length, which is, you know, in the case of the C14, is 3,911 millimeters. And that's where the location of the principal plane is. It's out, you know, located in front of the focal plane. It's 3,900, nearly 4 meters out in front of the telescope. Okay, and so that field angle, we don't care what's in the telescope producing it. Well, all we care about is it's that angle subtended at almost 4 millimeters, or 4 meters rather, of the size of the sensor, and that tells us the imaging angle, the field angle rather, out in object space.
Interesting.
Okay. So again, once you kind of lock these principles in your head and you start to understand it, and you know, and I've thrown a lot of stuff at you guys. If you haven't looked at a lot of this stuff before, 1 hour is pretty fast. We threw a lot of stuff there, so you may have to go think about it a little bit. But once you do, and you become kind of, it gets to be easy in your head. It's easy to calculate all these angles and things with just a calculator. You don't need to go look up any formulas or anything. It's really super simple. And that's the power of this whole thing.
I was gonna say these are probably all the equations that are behind the calculators we use for sizing out the Newtonian secondary. And
well, that's right. That's exactly, yeah. The Newtonian secondary is just the height of the marginal ray and the chief ray, and that, of course, is going to give you the semi-diameter of the minor axis of the diagonal in a Newtonian, and that's for zero vignetting. Now, you don't always build a telescope for zero vignetting, so you have to be a little careful. But if you want zero vignetting, that's how you calculate the size of the secondary, and it's super easy. You can draw it out on a piece of paper. And in fact, if you got AutoCAD, you can do it in 3 minutes and just measure it off the screen once you've drawn it.
So just to touch on that point, you said the size of the secondary is going to be the sum of the primary and the marginal rays?
Well, the sum of marginal and chief rays.
Chief ray.
Yeah.
Okay.
Yeah. Yeah. So remember, the chief ray is that ray that defines the center of the off-axis bundle of rays. Okay. So and remember, the chief ray passes through the stop, it passes through the exit pupil, it passes through the entrance pupil. Okay. And again, if you practice making some of these drawings, you may get a little confused. You can send me an email, I'll help you through it. but once you get used to it, it's pretty simple to figure out how to trace the chief ray, and then you add that chief ray height to the marginal ray height, and that's the minimum size for zero vignetting for any aperture or mirror or anything you put in the system.
So that is so that is to prevent vignetting within a system, but then how do we further take into account aberrations that may be produced by the secondary? Can you make modifications to the size of the secondary to prevent aberrations from happening, say, on the outside of a field?
Yeah, that's a little bit different topic.
Okay.
So typically, I mean, let me just pick on the Newtonian for a minute. I mean, you could pick on the Schmidt-Cassegrain as well, but in the Newtonian case, we've got a flat mirror, and that mirror needs to be very flat in order to control the wavefront going up to the imaging system. And it's at 45 degrees, so there's some caveats about that. But first order properties don't talk about how much aberration you would create with that mirror. We gotta go beyond that, start talking about interferometry and the shape, and we can get into sort of physical optics a little bit, talk about what happens there.
Okay.
Yeah, so that's a little bit beyond that. I mean, I'm happy to talk about that stuff. It's a little different than what we were talking about tonight.
I think I might just bug you on cloudy nights for a little bit.
You're welcome to.
All right, sounds good.
No,
I don't want to be a dictator here on this call and monopolize all the questions.
No worries, no worries. You can tell I love this stuff. It's an awful lot of fun.
I think a lot of us love this stuff. That's why we're here today.
Well, that's right. I'm impressed you guys are all here doing this on a Sunday night on Memorial Day weekend. So we almost be a bunch of techno geeks doing this.
Yeah, my fiance, she's laughing downstairs and mocking me, so I had to come upstairs.
Yeah.
Well, we're not imaging because of all the fireworks and bonfires, right?
Right.
It has nothing to do with
rain.
all the clouds.
Yeah, exactly. It's all rain here.
Yeah, tonight I got to get up early, so it's a good thing it's cloudy tonight. I'm happy it's cloudy. This is the one time I'm happy it's cloudy. I told my son I'd do something with him crack of dawn tomorrow, so it's the first time I'm happy about cloudy nights, but it's been cloudy here forever.
So I have a question that's somewhat related to the topic at hand, but just more towards the education. So if I wanted to move towards a career within optics, you said that you had your undergraduate in astronomy and physics. Now, is there anything that is more specific that is tailored to move into?
Absolutely. Yeah, absolutely. My degree is from the Optical Sciences Center at the University of Arizona. It's actually called the College of Optical Sciences. When I went there, it was a department. It's since become its own college. But they offer undergraduate degrees. They offer master's and PhD level degrees as well. And they do optics in everything ranging from optical engineering, which was really what I studied, to optical physics, which is interaction of light with matter, a lot of quantum optics, so it's a lot closer to physics. But they're doing all kinds of things. I mean, it's an amazing place. The next time you're in Tucson, you got to go stop by there. There's one of the professors there is building the most amazing 3D glasses you've ever seen in your life. And the big mirror lab, Jim Bird's working on the big 8-meter mirrors. There's an awful lot of stuff going on.
Awesome. Thank you.
So that's one. In the way, I shouldn't just say that. There's also University of Rochester, the other school, over in Rochester, New York. There's another school central in Creole in Florida. So there's schools all over the place for doing optics, for getting a formal degree. And then there are a bunch of people who get into optics from amateur astronomy. I know a fella at the Lunar Planetary Lab who started out building automated remote telescopes, and he interviewed over there and he got a job building remote telescopes and telescopes for spacecraft. So you don't necessarily need a formal background in optics to get a job there.
No, I just hate my job, so I want something new.
Well, I tell people all the time. In fact, I've helped a couple guys, one guy in particular on cloudy nights, who wanted to get into the PhD program. I actually took him down to the Optical Sciences College in Tucson and got him a tour. And I don't think he's decided to pursue that degree, but he had an awful lot of fun and he was impressed. And I encouraged him to get into the program, and I've done that in with a few different folks. thinking about pursuing an education. But optics is great. I mean, you don't end up hating your job. It's too much fun.
No, definitely awesome. So the other question that I have is the PowerPoint. Are you willing to share that with the rest of us, or is that something that
I'd be happy to. What I'll probably do is PDF it, though.
Okay, that's completely
I'd
fine.
be happy to do that. If you guys want to send me, I'm a little worried about getting inundated with emails from all over the place, but if you want to send me your private message via email.
Just email it to me, and I'll post it below the session.
Yeah, I'll do that. I'll do that.
Awesome, thank you.
Yeah. So if you, I'll send it to you, and you can take a look at it. That'll help you get started. You should practice some of that stuff that's in there, because it's when you first start doing it, it's easy when you see the examples, and then you try and apply it to something different, and it can be it requires a little thought to get it exactly right.
No, this is great. No, I love it, because I teach like minor physics to some of the little kids in the neighborhood, and that's some of the things that I do. So I just find it particularly interesting to play with myself. That's how I learn. I'm a tinkerer. Yeah. Rather than just simply read about it, gotta try it.
Sure. No, you'll have it's a lot of fun, and like I say, you can do a lot of useful stuff with it. It's totally amazing.
So cool.
Yeah. Well, good.
Thank you, John, for coming. I see we still have 6 viewers, so if you have your last chance to ask your questions, but if we don't get them soon, I'm going to end the session and thank everyone for coming. But remember, next week we have Stephen Ramsden coming in, solar imaging and outreach. And if you guys have been to a solar outreach event, he might have had something to do with it, because he runs lots of them, mostly on the East Coast. But actually, the Charlie Bates Solar Astronomy Project is nationwide, possibly even multinational. But I want to thank John again for coming. That was a great presentation. I know John's willing to come back for another. He's already offered, so we're going to hold him to it.
Well, I'd be happy to, Adam, and I appreciate the invite. Thank you.
Yep. Yeah, and a few more requests for that PDF. So like I said, send it right over to me. And guys, I'll post that as soon as it's all together, and you can read it once it's up.
I'll fire that off to you, Adam, and then you guys send me a request and give me a little bit of time, and I'll package it up as a PDF and fire it off to you.
All right. Well, right now I'm going to end the session. So thanks for coming. We'll see you guys next week. And the guys in the room are welcome to hang out just for a little bit.